Well, it's a great pleasure to be back here. I was last here in, I think it was 1973, but it's now 2011, and I'm too old to do that subtraction in my head. But you can probably work out that most of you weren't born when I was last here, and indeed probably most of your parents weren't born either. Anyway, but it is a delight, and I'm deeply honoured to be asked to participate in this inspired series. And I think the people who have endowed the series should be congratulated on their foresight and approach to understanding. And I'm going to talk this evening. I do know what Madeline Jacobs talked about early in the month. We exchanged correspondence, and indeed I've seen her script. And what I've done is to compile a talk which I hope springs from hers and takes it onwards, and you'll judge that for yourself. I'm going to talk about various aspects of education. I'm not quite sure why I've chosen glowing embers as my as the background to my slides, whether it means that education is more or less failing. And we're in the time when dying embers represents its... But indeed, I don't normally know why I do anything, but this is an example of something. Think of it as not dying embers, but igniting inspiration, igniting understanding, igniting everything that education is all about. I'm going to talk, if I have time, about various aspects. I'm going to talk about the importance of a scientific education. I'm going to talk about the importance of an education in chemistry, and I will go on to talk about the consequence of that, how to think about courses and so on. I will tell you what I think everyone should know about chemistry. Indeed, what I will do at that point is, for you chemists, undergraduate chemists in the audience, I will show you all you actually need to learn. And so everything else is just the way that your faculty fills in the time. I will think about planning courses, I will think about how to present concepts, and I will think about thoughts for the future. So that's the broad canvas of what it is I would like to talk about this evening. So let me begin by thinking about the importance of a scientific education, so then everything will spring from that. And really, I regard science as an extraordinary way of accounting for everything in the world, basically. And although in the past myth was mankind's attempt to discover understanding and comprehension, and the myths were delightful and entertaining, they were in fact empty. It was only when people like Galileo came onto the scene and started to go out into the world to discover what it was really like, rather than just sitting around thinking about what it should be like, that science suddenly surged forward. And what we're seeing several hundred years after that inception of the scientific method is a wonderful flowering of our understanding. And I think that it's a failure of culture if people do not understand the world in terms of the principles of science that are being discovered. One can accept that various scientific paradigms are temporary, in the sense that ideas that Galileo developed gave way to ideas that Newton developed, which in turn gave way to this wonderful iconic picture of Einstein, which developed. And no doubt in future, even Einstein will be overthrown with the developments in quantum theory and gravitation and so on. Perhaps, and let us hope, by people sitting in this audience. And I think we're waiting for the next great shift forward in understanding. But the fact that one paradigm of understanding gives way to another and then to another doesn't diminish the power of the scientific method. It really shows that the scientific method is a progressive approach to understanding. And I think so part of its power that scientists are revolutionaries, but they are conservative revolutionaries, and they build with caution on what has previously been established, and in fact that sequence demonstrates that. Another reason for the confidence of the scientific method is that it's scientific understanding is like a series of rivers that mingle, but where the rivers mingle, knowledge is not destroyed. They are enhanced, and you can think of obvious examples of that in terms of, for example, cosmology, where the very large needs to be discussed and formulated in terms of fundamental particles, that is, in terms of the very small. And so scientific rivers of understanding are complementary and supportive. They are not mutually annihilative. And I think that gives one great confidence in the current approach to understanding the world in terms of scientific principles. And I think also on this general theme of what science has illuminated, and the way that scientific understanding helps us to appreciate more richly the workings of the world. Just say a few words about what I regard as the great questions that science tackles and is starting, and in some cases fully explaining. So the core illuminations that science has provided, in fact, is of course the origin of the universe, which is one of the two great questions of existence. And it's rather wonderful that scientific measurements on the scale of centimetres on a lab bench can be extrapolated to understand cosmic phenomena, and that science is gradually moving towards understanding where the whole business came from. I could say quite a lot more about that, but don't have the time. But I think to realise that science is making progress with the deepest questions that have troubled humanity for millennia and it's doing it now, is an extraordinarily exciting thing. I think also the emergence of the biosphere. I mean, the fact that if you are looking for criteria by which you judge the greatness of a scientific idea, I think what you look for is an idea of extreme simplicity that has consequences of extraordinary broadness. And I think no better example of that is the principle of natural selection, which is so easy, so simple, yet accounts for the emergence of the biosphere, that extraordinarily complex collection of entities of which we are part. And so I think probably natural selection is probably the greatest ever scientific idea because of the power that springs from such a simple observation. But of course there are remaining problems which no doubt people here would consider themselves becoming in a position to tackle, which would be the transition, pregnant transition from the inorganic to the organic. How did organisms first emerge from inorganic matter. A great problem, not a problem that has yet been resolved, a problem that seems quite simple in a sense, and no great profound ideas were involved, but still difficult to understand. Another sign of the power of science, really. Science doesn't rush in where angels fear to tread. That there are many ideas about this crucial transition, but no one knows which of them, if any of them, is correct. And it's the cautious advance of science that prevents us yet from understanding this extraordinarily important transition. That one of the great discoveries, of course, of the last 60 years, I suppose it's about that really, is the structure of DNA, and understanding the nature of inheritance, which has transformed society. It's really showing the power that science exerts on our daily lives, that it's transformed medicine, it's transformed forensics, it's really transformed just about everything that anyone literally touches. And it's transformed biology from nature walks, which it was before 1953, to become a part of the physical sciences, and has given to biology all the power that transition represents. I mean, the physical sciences are powerful because they can render ideas quantitatively, and biology made that transition in 1953. I regard scientists as, as hewers of simplicity out of complexity. That they look for simple understandings which lie at the heart of complex phenomena. DNA, of course, is, and its four-letter code, is an extraordinarily elegant, simple solution. But nature has real trouble in interpreting the message. And what science does is to understand the way that nature, having selected a very simple way of transferring inheritance between generations, has to go about the business of decrypting that information. And it really got itself into a mess, and all the difficulties of childbirth and so on stem from that difficulty of translating a very simple code. But I want to move on from those general views about the illumination that science brings to our understanding of the world, to chemistry, and why it's important to study chemistry. I know that many people in the audience have already been converted to that view, but or at least came to this college converted, perhaps been deconverted in some ways. But I'll leave that on one side. But I know also that there are other types of people in the audience who perhaps need convincing that chemistry is the queen of the sciences, like myself. But I think the importance, to put it on a practical level, I think the importance of chemistry being that it is a central science, that it enables you to stand within the subject of chemistry and to look out into different directions. It enables you to look out into biology and through molecular biology to understand a wide range of biological phenomena. It enables you to, because it is built on physical principles, it enables you to look into physics and understand the phenomena that the physicists have discovered and are quite properly proud to explain. And It enables you also, because being part of the physical sciences, it depends on mathematics. It enables you to look into the realm of mathematics. So those of you who study chemistry are in an extraordinary, strong position for looking out over landscapes that are not just chemistry, that you can look out and embrace the whole of the sciences. If you start from some other viewpoints in the sciences, then maybe biology is too distant or physics too distant. But chemistry really enables you to appreciate fully the cultural impact of a wide range of sciences. So, and indeed, and I suppose this is really covering some ground that Madeline Jacobs covered. I mean, the contributions of chemistry are tangible, sometimes literally tangible. I mean, if you were to think of the world when there was only primitive chemistry, then it's rather a colourless affair. What chemistry has provided is colour and vibrancy to the everyday world. Its development of dyes and so on. Those of you who want to strip away the achievements of chemistry are invited to lie where this poor fellow is lying. I mean, one of the great contributions to civilization is medicine, and in particular anesthetics. And I think we should be proud that we are eliminating pain and ameliorating the sting of death when finally it comes. It's really chemistry does that, and we should be proud. I mean, chemistry provides understanding, and chemistry provides medical care. And I'm not quite sure which I would put as the more important, health or education. I suppose it's better to be alive but ignorant rather than being informed but dead. So basically, I suppose medicine is more important than education. And of course, as I said, the world has, chemistry has changed the texture of the world. The world feels different now from what it did 150 years ago. 150 years ago, then things were made of wood and things like that. Now they're made of synthetic polymers, and the whole texture, the whole feeling of the world is different through chemistry. So as you leave this room later, I hope, think of what you're touching and how the texture changed through the impact of chemistry. Of course, it's also transformed the possibility of sustaining populations, in the sense that through fertilizers and so on, one can grow thousands of times more food than primitive agriculture was able to. It's transformed fuels as well. I mean, fuels were originally sort of straw and hay, oats, but they've become, for better or worse, much more dynamic. The price to pay, of course, as you very well know in this part of the world, is the environmental pollution, but it's up to you, up to everyone, to try to judge whether this sort of cost is what you're prepared to pay for everything that chemistry has achieved. And what chemistry has achieved is represented, I suppose, by here. I mean, if you take the modern world and you strip it away, you ignite everything that is provided by chemistry, what you will get are bows and arrows and cavemen and so on. So I think this image will remind you of what chemists have achieved, and if you want to give up chemistry, then you go from where you currently inhabit to where you originally sprang from. Not something I would wish to do. Okay, I said I would talk about what everyone should know, and in other words, what, in my view, are the central ideas of chemistry that not only you should know, but the general public should know. You know, what is it that any cultivated human being who has the slightest interest in the way the world is organized and works, what is it that you should, what is it that they should know? And what I've tried to do in the next few slides is to identify the sequence, a series of ideas which I think are central to a chemical understanding of the world. Well, everyone knows that that's chemistry, but people should also be aware that, you know, the delights of going to say autumn day, but you might not understand the word. And you know, how does the general public can take greater delight, I think, from not simply responding to beautiful environments, but also to understanding how those beautiful environments emerge. And indeed, it's not just that sort of environment, it's a whole environment that one inhabits every day. In short, I think one I just took a photograph of dinner that we had just a few seconds ago. One can take simple delight from just looking at things, tasting things, touching things, just as you can take simple delight from listening to a piece of music. But in each case, you take deeper delight, if you're so inclined and your mood is right, to understand why the everyday world behaves how it does, how the colours emerge, how the textures emerge, how the fragrances emerge, and so on. Just like sort of understanding the structure of a Bach fugue or a Mozart quartet gives you deeper delight than simply lying back and letting your ears flap to the sound. So I think chemistry is in the business of enhancing delight. Those of you studying it might feel that's stretching imagination a bit far, but I think when finally you emerge through this tunnel of learning into the world outside, the later world, you'll see the richness of understanding that is provided. So, but I think the point of telling people about chemistry is to lead them across a bridge from ordinary macroscopic objects, which we're familiar with every day, to an understanding in terms of atoms and molecules at the other end of the bridge. And I think that serious courses in chemistry are ways of moving backwards and forwards across this bridge. And I think that sharing chemistry with the general public is also, at a different level, also the business of moving backwards and forwards across this bridge. Of course, you travel across the bridge in different ways, but still making connections between the macroscopic and the microscopic, the observed and the imagined underworld of atoms. And so there's I think there are 9 principles of chemistry, and I just very quickly run through them. First of all, there's the fact that sort of matter consists of atoms. Richard Feynman, before he died, indeed, he couldn't have said it afterwards, said that if there was a nuclear holocaust which wiped out everything except the cockroaches, and in order to give the cockroaches a boost by the time they were thinking about doing science and had evolved to that point. And he would leave a message carved on a rock, which he regarded as probably the most important clue to understanding the nature of the world, which is that matter is composed of atoms. Not quite sure he was right in that, but he was an interesting thinker. But as far as chemistry is concerned, then, of course, atoms are our currency. And you can't do chemistry if you don't believe in atoms. Ask Dalton. But so that, I think, is the first principle. The second principle is that we understand that elements lie in, are not like the British royal family. They're not a collection of individuals who don't talk to each other. That they form brotherhoods and families and so on, which we understand in terms of very simple ideas about atomic structure. The third is that in order to, when you bring those atoms together, then of course the key to it is the electron pair bond. And once you've got molecules, I think the shape is of crucial importance. I mean, in biology, biochemistry, in molecular biology, shape is of paramount importance. But it's also, I think, important at much simpler levels, in the sense that, if I were to identify the most important aspect of an atom, then I would identify its atomic radius. In other words, a quantitative measure of its shape in a certain sense, because so much flows from the shape, from the size of an atom. And likewise for more complicated systems. Go through this very fast because I've got quite a lot of material. And then once you've got molecules, and with particular shapes, the fact that they cohere enables you to make the transition from transition in understanding between individual molecules and the bulk materials and so on, in this case, of course, benzene. And then, taking a slightly different tack, I think one of the great unifying ideas of science is the conservation of energy. And at a very deep level, which I would go into if I had time, but wouldn't, this is really the fundamental reason for the causal structure of the world, the reason why one event is caused by another event, and so on. And also, the conservation of energy is crucial in chemistry because it's a kind of policeman on what can change and what cannot change, and so on. So I'd put this very high on my list of principal ideas. Of course, you chemists would know it as that most boring of all laws, the first law of thermodynamics. But I mean, if I had time to unfold the richness of the first law of thermodynamics, not only would I lose the audience, it would take too much time. So I won't say further about that. And of course, the reason why anything changes at all is because of the, if you like, that most wonderful law of thermodynamics, the second law of thermodynamics, that, broadly speaking, says that things get worse. And I will, in due course, come back to the second law, because I have a number of things I'd like to share with you about it. So the driving power, the driving force for any chemical process, of any chemical reaction, is this tendency of the world to become more disorganized and more disordered. But it doesn't do it in a rush, because molecules have got to overcome energy barriers. So the world didn't sink into some sort of soup and goo the day after it was made, simply because things suddenly got worse. Things get worse very slowly because of energy barriers, and that now enables beauty to emerge. and enables us to emerge. And sometimes beauty and us are the same thing, but of course not always. Principle number 8 is that that the tendency to collapse into disorder is held back and occurs very slowly. So all kinds of interesting things have time to occur. And then, of course, the actual process of reaction, I think I would, and I won't go into my thoughts here, but I would identify only 4 different types of chemical reaction. So there are only 4 processes by which the world is getting worse, basically. So in short, in my view, everyone should know those 9 principles. And I think there, in a sense, is the basis not just for communicating to the general public the nature of the world through a chemist's eyes, but also the informing, underlying the structure of courses that we put together for instruction. And I really, that's really my views on the structure of things. So that does lead me on naturally to that next step of how we plan our courses, and how we encourage an understanding of going from the macroscopic world to the microscopic world and vice versa. And what I've done here is to identify what I regard as the difficulties, which will always be in red, and the opportunities, which will always be in green. And it seems to me that a combination of identifying these and then elaborating those is the way that courses should be put forward. So it seemed that the difficulties seem to me in thinking about courses are that chemistry is basically a very abstract sort of subject, that it deals with intellectually intangible things like atoms, molecules, and so on. It uses mathematics, which puts some people off. I know that this is a college full of geniuses, so that's of no consequence here, but if you speak to people in other parts of the world, in the real world, I might say, then this is really an impediment to understanding. And also, the way that chemistry is really a very complex subject, because lots of principles are involved, sometimes appearing in conflict with each other. And you need to know a lot about chemistry before you can start making predictions. So these seem to me to be the difficulties of, in a kind of 3-ternary phase diagram, if you like. And I don't know where each of you would put yourselves, but I know you've been doing ternary phase diagrams, so that's perhaps relevant. But the opportunities are the fact that one can modify the curriculum appropriately, one can identify the core concepts, not those I did a few minutes ago, and one has the whole apparatus of graphical presentation now available, which a few years ago was not. And so really this is my combination of difficulties and potential opportunities that perhaps one should keep in mind when building courses. Going to deal with a few aspects of it. Abstraction. I think what I mean by abstraction, first of all, is that one's dealing with entities you can't see, so those are rather further down the line. You're dealing with energy that everyone pays a lot for, but that no one actually understands. I mean, what is energy, and how does it play a role in science, in chemistry, and this wonderfully mysterious quantity, entropy, that is in fact, in my view, much easier to understand than energy, but which everyone thinks the opposite. So that's the kind of abstractions that one should be alert to, and just a representation of what I have in mind. But graphics, I mean, now that we've got graphical procedures for displaying the insides of solids and molecules and so on, everything is made tangible. Everyone now can see that atoms and molecules are real things and that can be displayed, and I think the role of graphics is hugely important. Even for the second law. I mean, I think the second law is the most important law of science, which I'm prepared to sustain that, in the sense that it gives an understanding of why anything happens at all. And I think that's tremendously important. Of course, C.P. Snow, the English novelist, said that not knowing the second law of thermodynamics was like never having read a work by Shakespeare. Of course, totally meaningless in the modern world, where no one's read a work by Shakespeare anyway. But he did use it figuratively as a measure of scientific literacy. I have no doubt, by the way, that C.P. Snow didn't understand the second law, but you know, that's by the by. But it saddens me hugely to think that there are all those corpses out there who never knew the second law of thermodynamics. I think dying before you know the second law of thermodynamics is deeply distressing, in my view. And so I'm in favour of sort of educating pre-corpses so that they have a more fulfilled eternity. But everyone can, I mean, the second law of thermodynamics is said to be so difficult to understand. It's only because the person saying that doesn't understand it. Of course, we know that it's because that doesn't happen, but this does. And there's the second law of thermodynamics. In other words, things get worse. But I spent a couple of minutes on the way that I would present the second law to the general public, anyway, and indeed to prepare sort of freshmen to understand the significance of the second law, is to say, well, yeah, okay, things do get worse, but there might be a mechanism which links into that dispersal and enables you to build structure from where previously there was no structure. So this is the importance of the second law, that decay here can cause structure to emerge elsewhere. And that's all the second law is about. And it's about, then you apply it to, of course, whatever you want to apply it to. This might be the fuel in a car engine, which, when it burns, gives rise to carbon dioxide and water molecules which disperse, releases energy which disperses as there. This might be the actual engine, and this might be a pile of bricks which are driven into the form of a cathedral. So from dispersal in the engine, there might be structure emerging. This might be breakfast, and this might be your digestion of breakfast. This might be the sequence of metabolic processes in your body. This might be a collection of amino acids which are joined together to give you a polypeptide protein. So as you eat, so you grow. You can even take it more fancifully than that this once again might be dinner or breakfast or something. In your head, in your brain, there's a collection of, depending who you are, of random electric and synaptic currents and so on, which become organized into works of art, into scientific understanding, into deeds and so on. So in a sense what you've understood, and I think this is one of the great things about science, you've understood the connection between that great disperser in the sky. First time I've seen it since leaving England, actually, when I got here. through kind of a Japanese breakfast, to the processes that lead to organisms and the processes going on inside those complex organisms. So the second law, in my view, illuminates so much about the world. It's rather wonderful. Mathematics. I think the problem with mathematics is really a lack of preparation. Once again, extreme abstraction in many cases, which people feel uncomfortable with, and maybe the gap between concept and symbol. I don't have time to go into that. I think it's all overcome. I think mathematics now, the teaching of mathematics has become really, well, one has opportunities for doing rather wonderful things. So instead of doing it in a strictly analytic way like that, you can replace it by a more graphical procedures and so on. And I think the use of sort of graphical displays and of abstract concepts is very important. And I could say more about that, but time is moving on. So let me indeed move on. Let me talk about the role of visualization, because I think that, as I said before, I think that now that we have at our disposal graphical engines, that we've got rather powerful ways of transmitting ideas from one person to another, not only sort of being able to construct images of solids, but of molecules and so on. So everything become very graphical. And I think the importance of that is that talking about graphical images enables one to bridge sort of abstract ideas and tangible ideas. Many chemists are not abstract thinkers. Many chemists are visual thinkers, and being able to present concepts graphically, visually, is for them extremely important. And it's a shame to discard from a cohort of chemists people who struggle with the mathematics, when so much of chemistry is in fact highly visual and so on. So one has to be very cautious, I think, there. There's something else, though, that's important. I think thinking about the graphical representation of a concept or of a piece of mathematics is a very good procedure for educators, for instructors to go through when presenting material. That if you can take a mathematical formula, say, and think what it means graphically, then it deepens your understanding of what that formula is trying to tell you. So let me say, I think when I do the illustrations for books, and indeed illustrations for this presentation this evening, I've got a variety of rules in mind, and I just run quickly through rules that I'd like just to survey. That an illustration should really take you from, should be progressive abstraction, as I've expressed it there, that you take reality, you think of something which more or less resembles what's going on in terms of certain codes of drawing, but this is far too complex to carry around all the time, so you have to abstract it to something much simpler. So you always need to think of what the sequence of abstraction is in drawing a diagram. Likewise, you need to simplify focus, that you might think of water and hydronium and hydroxide ions in water like this, but they get lost if you had a real illustration, semi-real illustration. You need to abstract, and you need to realize that this abstract representation actually is a code for something much richer. Once again, the same sort of thing. That, once again, detail is sometimes overwhelming, and you need to find ways of progressively simplifying what you're actually trying to convey, so that when people see just a plain cylinder, then they should have in mind something much richer. I think that if you're drawing a graph, then it's always a good idea to be reminded about what it is that you're actually graphing. And in this case, just including an image of the molecule that you're talking about can really show that you're not just talking hot air, you're talking about real entities. So it's really the relevance of art. I think also the portrayal of data is very hard to assimilate something like that, but very easy to assimilate something where the data is represented in a more visual way. So it's the visual representation of data brings it alive, I think, and makes it more memorable. I think understanding approximations can be helped by visualization, so that if you've got this sort of gas phase reaction and a little bit of water is generated as well, you know you can ignore the volume of the water that is produced in this arrangement. So graphics can be used to inspire approximation, but they can also be used to delineate the limits of approximation, so that you might, in a series of approximations, end up, never mind what I'm showing there, but this typical sort of acid-base sort of problem, you might end up with results like that, but the exact solutions are more complex, and it's good to be able to realize that you really shouldn't be using the first graph in this region, but you can use it in this region. So using graphics to delineate the region of validity of approximation, I think, is very important. So those are some of the principles. I will get on now to the role of e-books. I did give a talk on this subject a couple of years ago, and I've just taken the beginning because times have moved on. I used as my theme 2001 Space Odyssey. And you'll remember the theme of the movie, which was that really ancient man, and a few ancient women in there as well, suddenly came across this object, which in effect transported them culturally into the future, that enabled them to build a space station. And then once mankind had got to that point, another object was discovered which projected them to Mars and the next dimension, and so on. And indeed, that's an analogy of what really is happening now, because instead of having a space odyssey, we've got a book odyssey, and that in ancient man and woman was really pushed into the direction of our current civilization by the development of the printed book and so on. So it was a wonderful moment for progressing civilization. And what we're just embarking upon now, of course, is the replacement of that by sort of electronic media and so on. And so we're really looking at the incipience of a new dimension, really. We're on our way to Jupiter in terms of the Space Odyssey. It's going to revolutionize our courses, and those instructors who think it's going to be the same for in the next 10 years and so on should have their heads examined. Anyway, this revolution is upon us, and I don't know how much time I've got. I've got 2 minutes, have I? Yeah, at least 5 minutes maybe. Yeah, thank you. I've only got 2 minutes of things to say, but I will take 5 minutes to say them. The advantages of paper books should never be lost sight of. I think a paper book, I mean, if you take something like the 0th edition of physical chemistry, you're confronted with this great wodge of paper, but you can see that there's quite a lot more to come, but in due course, you really do see that the end is in sight, thank goodness. But in an electronic book, you don't have normally that sense of achievement because you can't see yourself progressing in the same way. I think books are hard work because you've got to try to understand what the author meant, if he meant anything at all. And so I think it's very important that you struggle with concepts and don't have them just shoveled onto you because that's not the way of ingraining knowledge into yourselves. I think similarly, books make you use your imagination, and that you have to imagine what it is that the author was thinking. And you have to build up images of concepts yourselves, whereas in an electronic format, you might just be provided with them without having to think. It's like going to see the movie rather than reading the novel. And I think it's very important to read the novel to build up your own images of the characters, likewise in paper books. Disadvantages, of course, that they're slow to update, they're not interactive, the virulent second-hand market, and they're just a pain to carry around. But the advantage of e-books and so on is it's trivial stuff, really. They're interactive. You can summon a wizard to do your homework for you, basically, which is. And I think the role of wizards in e-books has got to be developed. I was going to show an animation. I'll skip that because I don't have time. Did I hear a groan? No. I don't know. I didn't do this one. I'll show it for Roy Casker's case. But I think the fact that an e-book can show you the dynamic processes that are occurring in chemical phenomena, rather than just showing a series of dead fish, but you can actually understand the dynamics of a chemical process. I think that's hugely important. Of course, this is information against time. An e-book has the advantage that it can be continuously updated, whereas a paper book is updated every 4 years or whatever. The problem for the author, of course, is that the ordinary book, paper book, you put a lot of effort into an edition, go on holiday, 4 years later put another lot of effort into the edition, whereas with electronic phenomena you're working continuously, and I think this is a serious impediment to people getting involved in this sort of thing. Customizable, of course. You can customize a paper book by doing that and then that. But you can see that electronic books, which are so adaptable and easy to use, you can choose your level of presentation, and you can use your energy, your level of help with particular concepts and so on. For publishers, they can sell in bits and pieces. You can, if you want an answer, maybe it'll cost you 10 cents. There's microcosting is going to come, believe me. If you want, understood on your behalf, it's going to be a whole $1. That might be worth paying for some concepts, I suppose. But certainly this sort of microcosting is going to emerge into publishers' market. I was going to talk about collaborative learning and indeed collaborative teaching, where you can sort of transmit information. And I'll go on to this, though. Embedded video. I had Al Capone on here, sort of trying to dissuade you from asking awkward questions in the front row. But time's running out on that, and I'll move on. For a publisher, e-books are rather wonderful, because you have a bomb built in that after a year you lose it. So there's no second-hand market. And that is highly attractive to publishers, of course. I think it's dreadful, because I think books should be your lifelong friends. So not only should this not happen, you should not sell them on to use them as well. I'm covering myself there, you see. Various issues. The trouble with publishers is that they're not very rich. And they're certainly not rich enough to use all the hugely complex and expensive games engines to generate graphics and so on. So normally when you look at a piece of academic gameplay, if you like, it's tedious in the extreme. Whereas people are brought up on fantastic visuals these days in computer games and so on. And as soon as they see something that's been put out in a low-cost way, then they think of it as an amateur presentation. It's a really dangerous aspect of future publishing for electronics and so on. Don't think that e-books will get cheaper, because they will have to be elaborate. And elaborate means a lot of development work. They will remain expensive. One of the problems is that it's very difficult to think that a single author will be able to develop the really fully interactive, vibrant e-book. So it will be done by committee. There will be kind of a loss of personality, which you think might be a price worth paying when you look at some personalities involved in writing books. But instead of a single voice, what you'll need, I think, my vision of the future is that you won't have authors. You'll have Steven Spielbergs and Stanley Kubricks and so on, who are the directors of the presentation rather than individual authors and so on. But we'll see. So aspects of the future. I'll just wrap up now because I've gone on long enough. Just one or two aspects. I think we'll have to adjust the way we examine. At the moment, you've got a brain. And this is all just going to be symbolic, and don't take this literally from now on. When you educate the brain, you sort of, let's pretend, change that hemisphere. But then you have to examine what you've fed in. And you tend, in my experience currently, to examine the other part of the brain. In other words, examinations currently do not examine the new modes of education that are emerging. And I think that a great deal of effort will have to be put into the development of examinations and tests that are sympathetic to the new ways of learning. We'll have to watch that. So what you really want is to homogenize teaching and learning and examining, which I try to represent by blending the colours here. That will have to come. I think it may be, and this is perhaps dangerous ground, I'd actually foresee the end of the lecture. And I think as soon as you've got electronic modes of communication, why bother to go to a lecture? Why go to classes and so on when you can do it all externally and interactively? So although instructors probably don't want to hear this. I think their days are numbered. I'm not going to put the number on it. I don't think it's as small as 10, but whether it's as big as 10,000, I really don't know. But don't plan for the far future, just. And also, to end on a positive note, I think electronic media in the future enable us really to globalize learning so that we can spread it to one of my own pet concerns, the sort of developing world, and helping to improve chemical courses, chemical education there. It means that, you know, on the savannah you will be able to enjoy education from places like Oxford, and indeed places like Harvey Mudd, and indeed the two can interact as perhaps I'm representing this evening. So anyway, let me come to an end there. What I've tried to do is to show you the issues that seem to me to underlie what currently are the challenges to education, in particular the education in chemistry, the rewards that can come from such an education, and a few thoughts about the future and where it's all going. But at that point, I thank you for your attention and come to a conclusion. Thank you.